So when we use the equation in this way, where we have present value is equal to future value divided by 1 plus r to the t, the term r takes on a different name and a slightly different meaning. We're no longer going to refer to r as the interest rate, and we're going to talk about it in terms of the discount rate. A discount rate is something that is specifically used to reduce the importance or numerical value of revenues and costs out into the future relative to ones that occur sooner. So we just talked about the time value of money and sort of derived that from a discussion of compounding savings accounts and how much money we need to have today to get to a higher value out into the future. And that numerically led into this equation, PV is equal to FV divided by 1 plus r to the t. And what that suggests is that the present value is always going to be smaller than the future value. And the time value of money suggests that future values are always going to be less important than present values. So that discussion is going to lead into another concept called discounted cash flow analysis. And this is going to be a bit more applied and a little less abstract. But this is a way to evaluate the economic viability of a project or compare multiple projects side by side to see which one is a better option. And the whole point here is that it puts all future profits, profits, remember, are revenues minus costs, in terms of their present value. So let's say profits are, in every year, are revenues minus costs. So money coming in, revenues, and money going out, or expenses or costs. So we discount future profits, so both revenues and costs, using a pre-specified discount rate, R, and the formula PV is equal to FV divided by 1 plus R to the T. Let's do an example. So let's say if I'm in charge of some sort of enterprise, and my profits today are minus $6 million. In other words, I'm either having to spend $6 million while I'm not making any, or I lose $6 million somehow. And then in the following years, I earn a profit of plus $3 million. And then in the following 2 years after that, plus $2 million and plus $1.5 million. How can we put that all in terms of a present value, in a single present value, if my discount rate is 5%? So let's go year by year and assign a present value for each one of those individual future values. So the first thing that we need to evaluate is what happens in year 0, or today. And I mentioned that we have a profit of negative $6 million today. So we're going to use this same formula. PV is equal to FV divided by 1 plus R to the T. So in each case, what we're looking for, what we're solving for, is PV. And so in year 0, we have T is equal to 0. And our future value is actually minus $6 million. And that might seem a little weird to think about what happens today as a future value, but it's just a special case in year 0. So let's say today we lose $6 million, so our FV is equal to $6 million in that first line. We're dividing by 1 plus 0.05. We said our discount rate is 5%. And we're multiplying what's within the parentheses to the power of t, which in this case is 0. So if you take anything to to an exponent of 0, you just get 1. So what we really have in terms of year 0 is minus $6 million divided by 1, and that just gives us minus $6 million. So that makes sense, right? So the present value of minus $6 million today is just minus $6 million. So first line is pretty easy to do. On the second line, we're looking at how to assess the present value of earning a positive profit of $3 million 1 year from now. So 1 calendar year from today, how much is $3 million worth if we got it 1 calendar year from today? So our future value is $3 million, and we're dividing again by 1 plus 0.05, and now we're taking that, what's in the parentheses, to an exponent of t, because we're looking at year 1, t is equal to 1. So in this case, we're simply dividing $3 million by 1.05, and so we get some value that is less than $3 million, implying that getting $3 million 1 calendar year from today is not actually worth $3 million. In this case, it's worth $2.86 million. So we can go to the next line. In year 2, our profits were $2 million. Our interest rate is again 5%. That stays the same. The only thing that's different here is the exponent t that goes on the outside of the parentheses. So here we're dividing $2 million by 1.05 squared. And when we get that, we get $1.81 million. So again, having $2 million of profits 2 calendar years from today is not actually worth $2 million. It's worth $1.81 million. Same thing happens in year 3. Our profits were $1.5 million. And we're to get the present value of $1.5 million 3 years from now, we're saying $1.5 million divided by 1.05 cubed to the third power, and that gives us $1.3 million. And then finally, in year 4, we're going to look at the present value of $2 million 4 years from now is $2 million divided by 1.05 to the fourth power, and that gives us $1.65 million. So takeaways here is that in years 1 through 4, our actual profits were all worth less than what we sort of said their nominal value was on paper, right? All those future profits are actually worth less if we put them in present value terms. In other words, if we discount them by 5%, according to how far out into the future we're going to experience them. So if we add up everything that we get on the right-hand side of the equation, that minus $6 million that we experience today, the $2.86 million that we in profits that we experience 1 year from now, and then $1.81 million 2 years from now, $1.3 million 3 years from now, and then $1.65 million 4 years from now. If we add it all up, we get a total of $1.6 million. So let's try a different example that's a little bit applied in terms of a specific power plant. So last time, all we talked about is where a utility would get money to build a power plant. And this time, we're going to really sort of plug in some numbers to evaluate the economic or financial performance of the power plant. So let's say that a new coal power plant has a capital cost. Again, that's sort of like the sticker price of $120 million. And let's say that we know that this infrastructure is going to be mostly financed, right? And so let's say that $20 million of that $120 million capital cost is going to come from shareholders' equity. So the utility is going to borrow $20 million from shareholders in year 0 to build the power plant. And then it's also going to sell $100 million in bonds to raise the remaining part of the capital cost. Then the bond is arranged with a third party to look like a normal loan. Remember, so you could plug it into an amortization calculator to get the annual payment and the percentage that's principal and interest, etc. So let's say the interest rate on the loan, which is the $100 million in bonds, is 5.5%. Return on equity for shareholders is 10%. The loan term or duration, that's the time over which the loan has to be paid back, is 25 years. Let's also say that the power plant has a lifetime of 25 years. And we can plug all of that information, the interest rate on the loan duration, and the principal on the loan, which is $100 million, into an amortization calculator. And let's say what we get out is that the annual payment, just for the debt, just for the $100 million in bonds, is $7.38 million. In other words, this utility would have to pay $7.38 million back every year for 25 years in order to pay that $100 million back that it borrowed with interest. So once the plant is built, let's assume it will have the following characteristics. It'll have some annual operating costs, let's say operations and maintenance, so keeping the lights on, paying employees to work there, fixing stuff that breaks, is $0.5 million per year. Let's say the fuel to operate the power plants, in this case would be coal, costs $30 million per year. And let's also assume that it's going to sell enough electricity every single year to make $42 million in electricity sales every single year. So we can start to put this in terms of a discounted cash flow analysis. So we want to evaluate what money comes in and out for this power plant in every single year. So in year zero, what we see is that the firm has a negative profit of $20 million, and that's because the shareholders are giving up $20 million to help fund this project. And then in years 1 through 25, the firm experiences annual costs of $7.3 million, and that's the principal and interest payments on the debt that it borrows initially in year zero to build the project. So that's the annual mortgage payment, in other words, on that $100 million debt that the firm acquires. Operational cost of $0.5 million, and then fuel costs, buying the coal for the power plant of $30 million. And we're going to assume that those annual costs are fixed. In other words, that the power plant will pay those every single year, year 1 through 25. Annual revenues are $42 million, and this is all the money that they're making selling electricity. So if we say we have annual costs and we have annual revenues, that gives us an ability to estimate annual profits, or revenues minus costs. And so if you say $42 million minus 7.38 minus 0.5 and minus 30, what you get is an annual profit of $4.12 million. Now, this is a really simple example for a lot of reasons, one of which is that annual revenues and costs don't change from year 1 to year 25. So let's assume here that the discount rate is the company's weighted average cost of capital. And so that's 6.25%. If you wanted to calculate the weighted average cost of capital here, you could go back to lecture 2 and find the formula for that. It's just the weighted average of the power plant's interest rate on its debt and return on equity for shareholders, weighted by the amount of the total capital cost of the project that's allocated to each form of financing. And so we have present value equals future value divided by 1 plus R, which is the discount rate, to the T. So it's a familiar equation, should be by this point. And so in this case, the interest, the discount rate that we're going to use is 6.25%. Okay, and let's do the math on this more applied example. Let's go year by year and evaluate what those future values are in terms of present value terms. Again, year zero is a pretty simple case here because we're losing $20 million. In other words, shareholders are putting up $20 million to help finance this power plant. And the present value of $20 million that we lose today is just negative $20 million. And you can see the math here. It involves dividing by something that's taken to the 0 power. And anytime you take something to the 0 power, because T is equal to 0 here, you end up with 1. And so we're just dividing minus $20 million by 1. So we get minus $20 million. In year 1, 2, 3, all the way through year 25, most of the equation looks the exact same. Our profits are $4.12 million. We're dividing by 1 plus 6.25% or 0.0625. That's the discount rate that we're using. The only thing that's different in year 1 through 25 in terms of the math is the exponent. And so you can see that the exponent goes from 1 to 2 to 3 all the way to 25, and that corresponds to the year that we're in. And you can also see that everything, despite the fact that everything in the equation is the same except for the exponent, the actual answer we get is declining in value. In the present value of year one profits of $4.12 million is $3.88 million. The present value of year two profits, again, $4.12 million, is only $3.43 million. And if we go all the way down to year 25, the present value of getting profits of $4.12 million in year 25 is less than $1 million, only $0.91 million. And so we can visualize kind of what this looks like. These blue bars just represent the discounted cash flows in every single year. And so in year zero, discounted cash flows are negative $20 million. That's shareholders dispensing $20 million to help pay for the power plant. And then we have $4.12 million in profits every year from year 1 to 25, but the actual present value of those profits declines gradually because we're discounting. And so the exponent around the parentheses in the bottom part of in the denominator of the equation, right? If we're saying present value is equal to future value divided by 1.0625 to the t, right? That t is getting bigger and bigger and bigger. And as that t gets bigger and bigger, the present value of the annual profits, or $4.12 million, gets smaller and smaller and smaller. So over time, the present value of profits declines as a result of discounting. And the present value of profits way out into the future are a lot less than the present value of profits that are in the near future, for example, in year 1, 2, 3, or 4.